Okay, everybody. I never feel really awesome about how to explain the concept of statistical power, just seeing how counterintuitive it is. But I've been especially bothered that I didn't get the point across in the YouTube lecture from yesterday. So I cooked this up. It's a version of what you had in the lecture, but it's tied to a concrete example that I'm hoping will make things a little bit more clear. Let's say that our study concerned how much data usage on a cell phone plan Verizon customers and AT&T customers used. Okay, so let's say that those are our two populations. Population one, the Verizon population, population two, the AT&T population. Now, I'm going to talk about this kind of just to make it easy in terms of a one-tailed prediction. I'm going to entertain the possibility that I can demonstrate that Verizon customers use more cellular phone data than AT&T customers. However, the null hypothesis here is going to be that Verizon and AT&T use the same amount. So let's just assign some numbers to that arbitrarily, just to keep ourselves grounded here. Let's say that the mu population mean of people on Verizon plans use 5 gigabytes, and the mu of people on AT&T plans also use 5 gigabytes. Of course, some people use more, some people use less, but if the mu of both of those populations is 5, then if we took a sample from Verizon and a sample from AT&T and subtracted the mean of both of those samples, you would most often get something that was 0. So this distribution that's on the slide right now is the distribution of x bar sub 1s minus x bar sub 2s under the presumption that the mu of both populations are equal to 5. So most often you get 0 or something close to 0, but because of sampling error, sometimes that difference will favor Verizon, sometimes that difference will favor AT&T. So it'll be on a distribution, and it would look something like this. Okay, so again, this right here is the distribution of x bar sub 1 minus x bar sub 2s that you would get if the null hypothesis was true and both populations were at 5. You drop a critical value in considering only that null distribution. The critical value is where the alpha proportion of this distribution begins. That is to say, the most extreme alpha of this distribution begins. So the thing to keep in mind here is that the critical value is determined completely by what is going on in the null distribution. This set of values, this area here, these are the extreme values that would cause you to reject the null hypothesis even when the null hypothesis is actually true. So alpha of the time, when the null hypothesis is true, you'll get an extreme result, and it would cause you to make the decision to reject the null. Here's another point. That critical value, where it is the only thing that determines your decision. Any result off to the right will cause you to decide to reject the null. Any result off to the left would cause you to decide to accept or fail to reject the null. So the decision is determined by where your result is relative to the critical value, not by which curve you're dealing with or which curve you're under. All right, now that we've got all that set up, now that we know what alpha is, we picked it arbitrarily, it's usually 0.05. We know where the critical value is, we know where the center of the mu of the null distribution is, we probably even know the standard error, we know all that stuff. Now we can consider an alternative hypothesis. So let's say that this is our specific alternative hypothesis, all right? Let's say that our alternative is that the Verizon people actually have a mu of 8 and that the AT&T people actually have a mu of 5. So that if you subtracted one mu from the other mu, the result would be 3 gigabytes of data. Okay, under those assumptions that the alternative hypothesis is true, you would get a distribution of x bar sub 1 minus x bar sub 2 that would look different than if the null was true. Here's what that looks like. All right. This is an alternative distribution. It doesn't center around 0, it centers around 3. If the reality is that the mu of Verizon is 3 gigs greater than the reality of AT&T, then most of the time when you took a Verizon sample and you took an AT&T sample and subtracted them, you'd get a value of 3, the Verizon being 3 gigs bigger than AT&T. But of course, not every time and not always exactly 3. But if the results that you got, if the null hypothesis was true, were on a curve, that curve would center around 3 and would have a certain amount of statistical noise associated with it. This gets us to the concept of the treatment effect. The effect of being a Verizon customer, or the treatment effect of being a Verizon customer, is 3 gigabytes. The difference between these two results is 3 gigabytes. The difference between the null assumptions being true and you typically get a 0 versus that the alternative assumption is true and you typically get a 3 is 3 gigabytes. That is the treatment effect. All right, so hopefully we've got all that. We know the distribution of results you get if the null was true. We have a different distribution of results that we would expect if a particular alternative is true, and we know how much separates those two assumptions. In this case, it's 3 gigs. Now we're going to talk about how that critical value, which was determined by the null, affects how you decide about things that come from the alternative hypothesis curve. So if the alternative is in fact true, there is a portion of those results that are going to be on the side of the critical value that would cause you to decide to accept the null hypothesis, that is, to fail to reject it. If you fail to reject the null hypothesis, or if you accept the null hypothesis, then your statement at the end of the day is that AT&T and Verizon have the same usage. That would cause you to have made a type 2 error. There was a 3 gigabyte difference there between your populations, but your hypothesis test didn't convince you that there was any difference at all. That area in red, its size, its proportion of that curve is beta. Beta is how big that is, okay? If you get a result that is in the beta area, you've made a type 2 error. Notice that whether it's a type 2 error or whether it is a correct retention of the null when it's true, you don't really know. They both resulted in the same decision, that you've retained the null, that you're on the left side of the critical value. Here's the other portion of the alternative hypothesis curve. Everything that is not in the red area, but that does come from a universe where the alternative hypothesis is true, is power, 1 minus beta. Power, then, is the proportion of results that you would get if the alternative hypothesis is true that would cause you to make the decision to reject the null hypothesis, right? So in this case, 1 minus b is power. 1 minus b is always power. That's not just in this case. And it represents the probability that you reject the null if mu of the Verizon population minus mu of the AT&T population was actually 3. So that's another run at something that I tried to get across in the last lecture. Hopefully this will be something that is at least somewhat useful when you tackle your in-class assignments. I will see you tomorrow for questions during class time when those in-class assignments go up. Take care.